All right, so today's plan, we are planning to finish up simplifying using square roots, really just two more little questions at the end of that section. And then our main goal for today is to get a good start on the percents chapter, chapter 6, talking about kind of what is a percent. Um, I think we'll see that percents, they might seem a little bit complicated or complex at first, but it's really just material that we've already covered, either fractions or decimals, kind of rephrased in a slightly different way. So uh, we've kind of put in a good bit of hard work over the last couple of chapters. And I think we're going to see that pay off here, that hard work over the last couple of chapters is going to make, I think, chapter 6, I would hope, pretty accessible. And then also looking at solving applications of percent. So solving equations that have percents in them, or solving kind of real world examples that that result in percent equations. So a reminder that Unit 2 exam is this week. I know a couple of folks have had some Examity challenges, but I think everybody who's reached out to me with questions has been able to kind of get Examity up and running, either with my help or with the help from the Examity folks. So if you have any, issues with Examity, let me know. But it does seem to be working pretty smoothly for everybody that I've been in contact with. It's available, the exam is available from 9 a.m. yesterday morning through 11:59 p.m. this coming Sunday the 3rd. So, and as I mentioned before, make sure that you don't wait until the last minute to take the exam. There are no due date extensions on the exam because it's open for a full week. So I'd recommend planning to take it no later than, say, Thursday evening, maybe Friday morning at the latest, because if something does go wrong, if you have a power outage at your house or an internet outage or something like that, or anything like that happens, that gives you a good bit of buffer to either get that worked out or find an alternative way to take the exam. Maybe come onto campus or something and use the campus internet if that's an option, or go to a local library or whatever it may be, right? There's lots more options, say, during the day on a Friday than, say, on Sunday evening. The material for the exam is sections 3.3 to 5.5. Sample exam is available. Note the difference. I think there was a question or two about the difference between the sample exam and the Examity practice exam. The Examity practice exam is really only there for you to practice the Examity portion of things. So getting you logged on to Examity, get an account set up, make sure that the screen recording and webcam recording kind of is all working correctly, that you can open the exam kind of in collaboration with Examity and so on. That's the goal of the Examity practice exam, to practice the Examity process. The sample exam is meant to be kind of a sample of the actual exam. That's really, it's an exam that's quite similar. It's academically very similar to the actual exam. It's not timed. It doesn't have the password screen. You wouldn't log into Examity to start the recording to open the sample exam. You just kind of go into the sample exam. But the purpose of the sample exam is that it's going to be quite similar to the material that's on the actual exam. So if you go through the sample exam and you feel comfortable completing that material in that time, and you are happy with your grade on it, then you're probably well prepared for the actual exam. And you can use scratch paper and pen pencil on the exam, but no open book. It's not an open book exam, no notes, no calculators as well. I should explicitly put that here. No calculators or other technology, other than, of course, WebAssign that you're taking the exam on, and Examity and all that, but no other tech that's assisting you with the map. I think that is all that I have to say on the administrative side of things. Any questions on any of that?
I have a question. I just got in.
Yeah.
I didn't know it was updated our CCAC, and I was confused. And I just got here on for the exam. Do we have to make an appointment?
I should not have to make an appointment. Note that so the way that we are using Examity is with the automated setting. Now there are some faculty who use the live proctoring setting where there's like an actual person on the other end of what's essentially the same as a Zoom call, and they'll like tell you the instructions and they'll like tell you what to do and all of that. Um, I don't do that because I found that to actually cause a lot of tech issues for students in the past. So we're just using the fully automated version where you just log into the system and start up the screen sharing in the webcam and it just makes a recording. So for that, you don't need to have an appointment. I think it might still ask you to schedule an appointment, but I think you can like basically schedule the appointment for like right now and then just take the exam or something, or you might be able to just open the exam. Um, but for the live proctoring, so for other courses that use Examity, you might have to schedule more in advance so that they make sure, because if you have a person on the other end, they need to schedule when different people are going to be available and all of that. But for our course, you should not have to do that. For other courses, you might have to. So it is dependent on what the instructor chooses, what level for their particular course, but we're using the automated version, so scheduling shouldn't be an issue.
Okay.
They're asking for a password for the what's it called exam.
Yeah, for the Examity practice exam or for the
Mm-hmm.
yeah, so that's the password that the Examity browser extension will enter for you.
And where do you find that at?
If you want to pop into office hours, we can kind of chat about
All
that.
right,
Yeah,
I'll see you after class.
yeah, sure. Any other questions on anything? Okay, let's give me 1 second here to get this. There we go. All right, let's jump into it then. Oh, quote of the day for today. Actually, two quotes related to a common theme, at least in my mind, at least the way that I think anyway. One is by the philosopher Friedrich Nietzsche from the early 1900s, and comes from his book Beyond Good and Evil. And there's a section of his book where he just has kind of a listing of, aphorisms or little sayings. And this is a pretty famous one. He wrote it in German, so it's been translated in several different ways. But but it says something like, whoever fights monsters should see to it that in the process he does not become a monster. If you gaze long enough into the abyss will gaze back into you. And from the Silmarillion, I think a similar kind of idea. The Silmarillion is the kind of world building book for Middle Earth for the Lord of the Rings and the Hobbit series. So it's kind of like there's Lord of the Rings and the Hobbit, and it's a little bit of like a prequel to that, like from the creation story through um, through the age of man or whatever you want to kind of call it. And in the Silmarillion, there's a quote that for those who will defend authority against rebellion must not themselves rebel. Right. So if you start kind of fighting against some idea or principle or something based on a certain value system, uh, the fight can easily become the principle, right? You can easily start engaging in the fight for the purpose of the fight rather than for the purpose of protecting a certain system of values or whatever it may be. And I think these are at least one point of view of these two quotes is cautioning folks against doing that. Um, maintain the right perspective from the original value system. Um, don't let the fight kind of become the value that you want to carry on. Okay, so wrapping up chapter 5, a couple, or, well, I guess one more example, just kind of two perspectives on it. Let's simplify each of these following square roots. And here we have two different square roots that might at first glance look like they might give the same answer, but we're actually going to see that they don't. One of them is square root of 25 plus 144, where the 25 plus 144 is all under the square root. And the other is square root of 25 plus square root of 144, where we have two different square roots added together. So the square root of the sum versus the sum of the square roots. Here we should probably remember that we have order of operations, parentheses, exponents, multiplication and division, addition and subtraction. And exponents kind of include roots. So I kind of sometimes call it like PERMDAS or something, I don't know. So exponents, square roots kind of get lumped in with exponents. Really, a root is an exponent. That's something that we maybe come to appreciate a little bit more in Math 108. But yeah, so basically a square root acts kind of like an exponent. And I think we saw that a bit last time where we saw that square roots were kind of really intricately tied to squaring, which is clearly an exponent. Okay, so square root of 25 plus 144, if we have this kind of bigger operation of like an exponent, we can think of this almost like it was, say, 25 plus 144 squared or something like that. Not exactly the same. I don't mean to say that these two are equal, but I mean, kind of somewhat analogous. Right? Our exponent comes higher in the order of operations, but we want to kind of simplify the inside before we apply the exponent because the exponent also kind of, in a sense, implies a grouping symbol. And that's really what we're seeing here is that when we have square root of 25 plus 144, we're kind of saying do the square root operation on 25 plus 144. So there's kind of an inherent grouping here. This 25 plus 144 are kind of like treated as grouped together. They're treated as though they're in parentheses. We want to do that sum first, and then we want to square root. So 144 plus 25 is 169. And then if we ask, well, what is square root of 169? Well, let's look at, say, n and n squared for different values of n. Well, 10 squared is 100. 12 squared is 144. We might kind of know that from like our gross 12 dozen is 144, or we could multiply 12 times 12. So we need a little bit more than 12. If I go up to 13, if I overshoot, then I'll know that the answer is between 12 and 13, or what is 13 squared? 3 times 3 is 9. 3 times 1 is 3. 1 times 3 is 3. 1 times 1 is 1. Oh, well, 13 squared is exactly 169. So the square root of 169 is 13. And I think I've gotten a bit sloppy with my language. I think I warned you that I probably would. When we write this radical symbol, we mean the principal square root, the positive square root of the number. We talked last time about how, say, the number 169 really has two square roots, 13 and negative 13, because negative 13 squared would also be 169. But when we write the radical symbol, we mean the principal square root, the positive square root. And typically, if we just say the square root, the kind of implication of that phrasing is the positive square root, the principal square root. If we compare that to, say, square root of 25 plus square root of 144, well, I know that 5 squared gives me 25, so square root of 25 is 5. And I know that 12 squared, I saw over here, gives me 144. So square root of 144 is 12. And 12 plus 5 is 17. I get a different answer if I do square root of 25 plus square root of 144, or square root of 25 plus 144. If I add first, then square root, or if I square root each term individually, then add, I get a different answer. So I do have to be careful with this and respect the order of operations here. Are there any questions in on anything in chapter 5, whether it's something on decimals, something in square roots, anything else. Okay. So now starting into chapter 6, percents, and starting with 6.1, just some basics of percents, understanding percent. So a percent is a ratio whose denominator is 100, and we use the percent symbol to denote percent. Note that percent means basically per 100. I mean, if you think of a cent in your pocket, like you might have dollars and cents, right? 1 cent is 1/100th of a dollar. Or you think of like centennial or like centurion, like a Roman centurion, there were 100 of them. Or I think a centurion was in charge of 100 soldiers. So things like that, or, you know, going back to Latin, this prefix cent kind of has to do with 100. And we use the percent symbol to denote 1/100th. The percent symbol kind of, in essence, denotes this denominator of 100. So let's write each of these percents as a ratio. Your book has like, or the OpenStax book has like 4 questions that are like this, and they're all about unemployed people, and they have like, what, 4 questions that are all about, you know, community college first year freshman or something, or so I don't know. I guess us math people are a little bit less creative than some other disciplines, but so I tried to come up with some other, you know, slightly different ones. But in 2015, among the unemployed, 29% were long-term unemployed. So this is my percent that I'm interested in, 29%. If I write it as a ratio, remember, a percent is a ratio with the denominator of 100. So 29% means 29 over 100. Right? Again, we can kind of think of this percent sign. This is kind of somewhat loosely stated equals here, but it's fairly accurate. I can replace percent with 1/100th and multiply those and get 29 100ths. Or I could write this as 0.29 if I chose. Or I might say that of the 24 students in a class, 75% earned an A on the assignment. That's my percent. I could write it as a ratio, 75 over 100. I could write it as 0.75. Or I could write it as a simplified fraction. 75 over 100 is 3 divided by 4, 3/4 after I divide out, say, one factor of 5, and then maybe another factor of 5 after that. If I have a ratio, say something like 42 out of 100 first-time freshman students attend a community college, I could choose to write that as a percent. The ratio 42 out of 100, this is a ratio with the denominator of 100. I could rewrite this as 42%. So 42% of first-time freshman students attend a community college. Or 60 out of 100 nursing applicants receive their degree at a community college. %60 of nursing applicants receive the degree at a community college. Now, as a bit of an aside, I might choose to write something like 3 out of 5 nursing students or nursing applicants receive the degree at a community college. Well, 3 out of 5 as a ratio is just 3/5. I don't want to say that this is like 3%, right? This is a ratio, but the denominator is not 100, so I can't write it directly as a percent. But I can make that denominator 100 by, say, multiplying it by 20, and I maintain an equivalent fraction as long as I multiply the numerator by the same factor. 3 times 20 is 60, and 5 times 20 is 100, and now I can write this as a percent. So I could be given a ratio that is not naturally in terms of 100s, not necessarily 60 out of 100, but 3 out of 5 maybe. And I could convert that to a fraction with a denominator of 100 using the equivalent fractions property. And then I could write that as a percent. Okay. So let's convert each percent to a fraction and simplify, and also convert to a decimal. So 78%. Converting to a fraction is 78 out of 100. That percent just kind of means over 100. As a decimal, I see that this is 0.78. 78 is like 78.0. And then dividing by 100 just moves the decimal point 2 to the left. Or I could think of this, so this would be writing it as a decimal, or I could keep it as a fraction and write it as a fraction in simplest form. I see that 78 and 100 are both even numbers. They share a factor of 2. So 39 times 2 over 50 times 2. My factors of 2 can divide out. 39, well, that's 3 times 13, and 50 doesn't have any factors of 3 or 13, so 39 over 50, that's my fraction in simplest form. So I could talk about 78% or 39/50ths or a proportion 0.78. Those would all be equivalent ways to talk about the same thing. What about 135%? Well, similarly, I have 135 over 100. I could write this as a decimal, 1.35. 135% is more than a whole. Like if I have 135% of, of a pizza, I have like one whole pizza plus some extra. So that's 1.35. Or I could keep it as a fraction. Can I simplify it all? Well, it looks like there's a factor of 5. So it looks like I have 20 times 5, and I'm going to write that this way. Now that we've got decimal points floating around everywhere, I'll try to use parentheses to denote multiplication instead of dots because it's a little clearer. So I write the dot a little bit too low, it might look like a decimal point. And 135, well, that's like 100 plus 35, or 20 times 5 plus 7 times 5, or my distributive property used in reverse, that's 5 times 20 plus 7. I think that's 27 times 5. My 5s can divide out, and I have 27 divided by 20. Well, 27 is 3 times 3 times 3, and 20 has no factors of 3. So 135% can be written as 1.35 or 27/20ths. Or I suppose if we really wanted to, we could write it as 20/20ths, or 1 plus 7/20ths. If we wanted to write that improper fraction as a mixed number, if we would prefer that, we can do that as well. It's 1 and 7/20ths. What about something like this, where I have a decimal number with a percent after it, 46.4%? Well, again, we go back to our definition. What is this? 46.4 divided by 100. If I wanted to convert this to a decimal, I would take my decimal point, the divided by 100 says move it 2 places to the left. As a decimal, that's 0.464. Or as a fraction, I don't know, I could leave this like this, I suppose, or maybe I could make it 464 out of 1,000. Trying to make it whole number over whole number, I can maybe simplify it a little better that way. I can divide out a factor of 2, so that would be 232 times 2 over 500 times 2, and my factors of 2 divide out. I note that I still have an even number in numerator and denominator. So this is going to be 116 times 2 divided by 250 times 2. I can divide out another factor of 2. 116 over 250 is still two even numbers. So this is going to be 58 times 2 over 125 times 2. And I can divide out the 2's again. 125 is 5 times 5 times 5. And 58, well, 5 is not a factor of 58. Right, 58 divided by 5 would leave me with a remainder. It would be 11 with a remainder of 3. So 58 over 125, that's the simplest I can get. So this also makes a nice review of some of our fraction material from a couple of chapters ago, so a little bit of our decimal material from last chapter. And something that might look really strange is like a mixed number with a percent, like 8.5%. You don't see this all that often, but you see it a lot of times in financial settings, like say your mortgage rate might be like, 3 7/8% or something like that. So you see this in those kind of settings, or maybe like sales tax, like 7.5% sales tax, something like that. So what's 8.5%? Well, that would be like 8.5 over 100. I take the number that's in front of the percent sign, divide it by 100. I'm a little bit stymied here, but I suppose I could take two different perspectives. I could go the decimal route, and I could note that 8.5 is 8.5. So 8.5 over 100 is 8.5 over 100. I need to move the decimal point 2 places to the left, so I need to put in a buffer 0. And I get 0.085 as a decimal. Or I could go the fraction route. 8.5, well, 2 times 8 is 16 plus 1 is 17. So 8.5 is 17 halves. Divided by 100, or that's really divided by 100 over 1. I have fraction divided by fraction. I invert and multiply, or multiply by the reciprocal, whatever way you would like to say it. 17 halves times the 100 over 1 flips and gives me 1 over 100. Or this is 17 over 200. 17 is a prime number, and it's the only factor in the numerator. So, and I don't have a factor of 17 to the denominator for it to divide out. So this is in simplest form. So I could write it as 17 over 200, or 0.085 for 8.5%. Sorry, my lawn guys are here today. I don't know if you can hear the weed whacker in the background. But any questions on any of this? Okay. So next up, convert each fraction or decimal to a percent. So we converted from a percent to a fraction or decimal, we go the other direction. So if I have 0.18, I want to rewrite this as a fraction with a 100 on the denominator. So how do I do this? Well, with a decimal, I multiply by 100 divided by 100. And I want to keep the 100 on the denominator. So this is going to be 0.18 times 100 divided by 100. I don't want to like get rid of this. I don't want to simplify it, or I want to keep that 100 in the denominator. I don't want to touch that because that's what's going to turn into, where was it up here? That's what's going to turn into the percent sign. So I don't want to mess with that 100 in the denominator, but I want to get everything else as simple as I can. So I would like to multiply my numerator 0.18 times 100. Multiplying by 100 just moves my decimal point 2 places to the right. Right? Dividing by 100 moves it 2 places to the left. Multiplying moves it 2 to the right. So this is 18 divided by 100. I have a 100 in the denominator. I can basically just exchange that for a percent sign. So what do I have? 18%. 18 per 100, or 18 over 100. If I take 1/5, for example, I actually have two approaches. I could convert to a decimal and then take kind of this approach up here, or I could leave it as a fraction. Let's keep it as a fraction first. All right, so I have the fraction 1/5. And remember, if I'm going to convert to a percent, I need a denominator of 100. Can I find an equivalent fraction to 1/5 with a denominator of 100? Well, 5 needs to multiply by 20 to make 100. I multiply the denominator by 20. I have to multiply the numerator by 20 as well. So I have 100 in the denominator now, and 20 times 1 is 20 in the numerator. Again, I don't want to like go and simplify now or something like that. I kind of unsimplified on purpose because I need this 100 in the denominator. But now I see that that 100 in the denominator can kind of turn into the percent sign. And 20 hundredths is 20%. So this would be one strategy. I could leave it as a fraction and work with my fractions to get an equivalent fraction with a 100 on the bottom. That worked pretty nicely here. There might be other situations where that doesn't work so nicely. Or I could look at a decimal-based approach. So I could think of 1/5. Well, 1/5 is 0.2, right? If I went over here and did like 1 divided by 5, and 1.05 goes into 10 twice, 2 times 5 is 10, 0, nothing to bring down, 0 remainder, 1/5 is 0.2. So I could do the long division. I know I did that really quickly, but you could do this, carry it out, more diligently and carefully, but I would get 1/5 is 0.2 as a decimal. And as a decimal, I want to, just like above, multiply by 100 over 100. I don't want to do anything to this 100 on the bottom. It's important that that stays as a 100 so that I can later on convert it to the percent sign. But 0.2 times 100 is 20. 20 over 100 gives me my 20%. So I could reimagine the fraction as a decimal. Sometimes that will be more helpful. And then convert that to a percent, or I could stay within the fractions realm and get an equivalent fraction with a 100 in the denominator and make that my percent. Either approach works fine here. I think the fraction approach is probably a little more straightforward in this problem, but there might be other problems where it's a little nicer to convert to a decimal and work in decimals. So if we look at, say, the number 1.35, and we want to convert it to a percent, well, similar to above, my goal is to get a denominator of 100. And I need to multiply by 100 over 100. Right, the reason I'm doing this is just multiplying by 1. It's not changing the value. I need to keep my denominator of 100. And in my numerator, I have 1.35 times 100. If I multiply a decimal by 100, that just moves the decimal point 2 places to the right. This bit here becomes the percent. And I get 135%. Any questions so far? Okay, let's I actually want to throw one more example in here. Just for fun, let's do like 2/9 or something like that. I thought I had an example like that, but I either must have forgot to copy it over to my notes on here or skipped over it or something. But let's look at 1 2/3, converting it to a percent. So 1 2/3. So I guess 1 2/3 is kind of like this 2/9. So maybe that's what I was thinking. But so 1 2/3, I want to write it as a percent. If I try to use an equivalent fraction form, so what does this give me? 5/3. Can I multiply by something on the bottom to get 100? Well, this doesn't work out so nicely, right? It's hard for me to find an equivalent fraction that has a denominator of 100. So as far as sticking in the fractions realm, probably not going to work so great here. But 1 2/3 is 1.6 repeating as a decimal. So as a decimal, 2/3 is 1.6 repeating. If I do 2 divided by 3, 3 goes into 2 0 times. So I need another 0 after the decimal point. 3 goes into 20 6 times. 6 threes is 18. Remainder of 2. Put in another 0, break it down. 3 goes into 26 times. And I see that I've made a loop here, a cycle, where I started with a 2, got a remainder of a 2, and then I'm going to get another remainder of a 2, and so on. So this is going to be 0.6 repeating for my 2/3. And then I just add the 1 on. So I want to make this 1.6 repeating times 100 over 100. And again, I want to hang on to this denominator 100. I don't want to do anything with that. I want to simplify the numerator a little bit. .6 repeating times 100 is 1.66, let's say 6 repeating times 100, just giving ourselves a couple more decimal places to work with. This 100 says move my decimal point 2 places to the right. So that's 166.6 repeating over 100, or this would be 166.6 repeating percent. Or we might round this to the nearest percent and say this is approximately 167%. Right, 166.6 rounded to the nearest whole number. The next number over to the right, the tenths place, is 5 or more, so we round up. We get rid of all of the tenths place and below, we make those all zeros, and we increment our units place. The 6 goes up to a 7. So this is about 167%, or it's exactly 166.6 repeating percent. And let's look at an example like 2/9 here. An example that is less than 1 and isn't a super nice fraction to work with. So converting this to a percent, kind of similarly, if I tried to do the fractions thing, I want to multiply 9 by something, that's a question mark, to make 100. There's nothing really nice that I can multiply 9 by to make 100. Right? At best, this is going to be cumbersome to do. I'm going to end up with like fractions of fractional percents, and those can be kind of difficult to interpret what we mean by that. But I can convert 2/9 to a decimal. So if I do 2 over 9, 9 does not go into 2. Does 9 go into 20? Yes, it does. 9 goes into 20. 2 times 9 is 18. And does 9 go into 20? Yes, it does 2 times. And we see we have a repeat. So 2/9 is 0.2 repeating as a decimal. And I kind of see the pattern that for converting a decimal to a percent, I move the decimal point 2 places to the right and then make it a percent. So this is going to be 22.2 repeating percent. Or I could say that this is approximately 22%, say rounded to the nearest whole number percent. Any questions on this? All right, let's look at an example here. This is kind of a riff on one of your textbooks questions. I didn't like the textbook question, so we're going to take a look at why I don't like the textbook question. So to help decide whether to watch a certain movie, maybe, you know, it's in the theaters and it would cost money to go and watch the movie, or maybe we just don't want to invest 2 hours of our time into a movie that we don't think is going to be enjoyable. Amelio consults 3 rating sites and gathers the following data. Site A has a rating of 4 out of 5 stars. Site B has a rating of 3.5 out of 4 stars. And site C has a rating of 85% satisfaction. Let's convert each rating to a decimal and determine which site has the highest rating for the movie and what that highest rating is. And then let's ask ourselves, so this is basically what the textbook question is, more or less. Then let's ask ourselves, does it make sense to convert these all to decimals and compare in this way? And this is actually a pretty, I think, pretty applicable example. You know, if we're going on Amazon, we might see like whatever 72% of customers are satisfied with this purchase or would recommend this to a friend. And we might see that the thing is rated, you know, 4 out of 5 stars on the star rating scale. You know, are those kind of equivalent metrics? So let's take each of these. So for site A, we take the ratio 4/5. 4 stars to 5 stars, the ratio of 4/5, we can see that this is going to be 0.8 as a decimal. And then our kind of shortcut for making a percent is to bump the decimal point 2 places to the right and make it a percent. Right, where did that come from? That just came from, we were always just multiplying that decimal by 100. All that did was shift the decimal point 2 places to the right from the 100 in the numerator, and then the 100 in the denominator becomes the percent sign. So site A has kind of an 80% rating, let's call it. Site B, 3.5 out of 4. I could actually keep this as a fraction, even though it has a decimal in it. I don't really want to do the whole long division, but I see that I can multiply 4 by something, need a little more room here, to make a nice 100 in the denominator. I can multiply by 25. If I do it in the denominator, I better do it in the numerator as well. So multiplying top and bottom by 25 gives me an equivalent fraction. In the denominator, 4 times 25 is 100. And again, I want to kind of protect this 100 and the bottom here. That's going to end up being my percent sign. So I don't want to do anything that would get rid of it. And now I can multiply 25 by 3.5. I usually would rather multiply than divide if I had the choice. So 5 times 5 is 25. 5 times 3 is 15, plus 2 is 17. 2 times 5 is 10. 2 times 3 is 6, plus 1 is 7. So this is 875. And remember, we're multiplying decimals here. So I have 1 decimal place, 0 decimal places. I should have 1 decimal place in my answer, 87.5. Does this make sense? 3.5 out of 4, is that the same as 87.5 out of 100? Yeah, that seems pretty reasonable, right? 3.5 out of 4 is less than 1. It's not 4 out of 4, but it's like most of the way to 1, right? 3.5 out of 4 is pretty close to 4 out of 4. And 87.5 out of 100 is less than 1. It's less than 100 out of 100, but it's kind of pretty close. So it kind of passes the gut feeling check. It seems like a reasonable answer. And 87.5 out of 100 is 87.5%. And then 85% satisfaction, well, that is just 85%. And I did actually just realize that I said convert each to a decimal. Let's convert each to a percent. So I see that the site with the 3.5 stars out of 4, its kind of equivalent percent rating would be 87.5%. And that would be higher than 85 or 80%. So site B would have rated it the highest. And likewise, site A would have rated it the lowest, and they would all be in the kind of 80 to 90% window. So maybe we'd feel pretty confident spending our time or our money on this movie if it seems interesting to us. Now, a slightly deeper question. We did this. I mean, we took these ratios, we converted them to decimals or percents, and compared them. Does it actually make sense to do this? And so I was a little peeved whenever I saw this problem in your in the OpenStax textbook, because I thought, well, it doesn't really make sense to do this. Why is that? Well, for star rating, typically the way that star rating scale is you can rate from 1 to 5 stars. So when somebody goes onto a star rating scale, like if you go onto Amazon and you really didn't like the thing that you buy, you thought it was a terrible product for the money, the lowest rating you can give is 1 star, and the highest 5 stars. But for, say, a satisfaction, well, typically there you would just give a thumbs up or thumbs down. Like, would you recommend to a friend, yes or no? And then the algorithm looks across 100 people or 1,000 people and says, what percent of them, if I take the number who said, yes, I would recommend to a friend, divided by the total number, express that as a percent, what percent of them would recommend to a friend? My lowest is actually 0%, right? It could be that everybody says thumbs down, I would not recommend. And my highest would be 100%. Everybody would recommend to their friend. Or on the stars scale, the lowest is 1 star out of 5, or 20%. 1/5 is 0.2. That's 20%. And my highest would be 5 stars out of 5, 1, or 100%. And this is a big discrepancy. So if I have a star scale from 1 to 5 stars, if I'm not able to leave a rating of 0 stars, which you very rarely are able to on these kind of like star scales or rate on a scale from 1 to 10 kind of scales, you're very rarely able to leave a response of 0. Well, these scales, the measurement is kind of biased upwards. It seems like the product is better than it is. Really, what we ought to do is, instead of thinking of this as 4 out of 5 stars, if we want to compare it to a satisfaction rating, we probably should subtract 1 off of the numerator and denominator. We probably should think of this more like 3 out of 4. So that's kind of a side note that doesn't have to do so much with the calculations and the computations, but more with how do we interpret data, right? Kind of like information literacy. If everything is on the same scale, if I'm looking at 3 different products or 5 different products and trying to decide which one to buy off of Amazon, and one has 4 out of 5 stars, and one has 4.2 out of 5 stars, and one has 4.7 out of 5 stars, everything is consistent there. Everything is on that same scale. If I'm converting between scales, I really have to ask myself what that conversion means. I wouldn't want to take a star rating and a satisfaction rating. I really wouldn't want to compare them against each other really at all. I would want to consider them 2 different measurements. They're probably, in fact, representing 2 different characteristics of the product. So I probably wouldn't want to compare these to one another at all. But if I did want to compare them to one another, probably would be more sensible to use something like 3 out of 4, because then I'm pretending that my stars go from 0 to 4 stars. And then my lowest kind of star rating would be 0%, and my highest would be 4 out of 4, 100%. That would kind of match with the percent satisfaction range of possible values. So it's a little bit of a side note, but you want to be careful about this stuff. And even textbook authors get these comparisons, that they miss things like this. In our statistics textbook, they quite often talk about, say, computing averages of things like earthquake magnitudes. Well, you can't do that. It's not the right kind of scale to compute an average. So really thinking deeply about what are we measuring, how are we measuring it, and if I want to make comparisons of things, does it make sense to compare these things as they are? Number one, does it make sense according to the mathematics, on a scale that goes from 20 to 100%, does it make sense to compare that to a scale that goes from 0 to 100? Probably not, just mathematically. And second, on a scale, in the sense of psychologically, is somebody's answer, somebody's interpretation of this question going to be in line with their interpretation of that question? Maybe, maybe not. So we should think a little more deeply about these kind of things before just trying to compare between different scales. Just because we see a ratio versus a percent doesn't mean that those things really mean the same thing. So just a cautionary tale. Okay. This is a kind of cool little example on star scales that I just thought of. Kind of a little aside, call it a brain break or something, I don't know. So I read the book, The Girl with the Dragon Tattoo, by, I think his name's Stieg Larsson. And it was recommended to me by a friend, actually a retired faculty member now at CCAC, one of our former math professors. So he said, "Oh, it's a great book. You got to read it." So I picked it up, I read it, and I was kind of like, I mean, it was okay. It wasn't great. But I thought to myself, okay, it's a trilogy. Should I read the second one? Right? Should I invest the time and effort into reading that, or should I read something else? So I went to Amazon, I looked up the ratings for the first one. I'm thinking if the second one is a lot better, right? Maybe the story really develops in the second one, and I've just kind of gone through the slog of the first one that kind of built up the characters and all that, and the second one and the third one are where the real interest is. So thinking maybe that's a possibility. So I look on Amazon and I see the rating for the first one is, I forget exactly what the numbers were, but it was something like, say, 4.4 stars. Then I look at the second one and see that the second one is rated like 4.7 stars. And I thought to myself, oh, wow, like maybe the second one is just really that much better than the first one and it's worth it to read it. And same with the third one. The third book in the trilogy was also rated like 4.7 or 4.8 stars. And then I realized that the star rating scale is not kind of independent, right? It's not independent between books. In other words, if I read the first book and I thought it was a horrible book, I rate it as like 1 star. Am I going to read the second or the third book? No. If I thought it was a terrible book, which I didn't think it was terrible, but some people might have thought it was terrible, they're not going to read books 2 and 3 at all. So the people who dislike book 1 the most, who might be kind of a more random sampling of the population, they're not going to rate books 2 and 3 at all. There's a survivor bias there. We talked about survivor bias last week, I think, in one of the quotes. So the people who make it to book 2, who read book 2 and kind of survived to rate book 2, are the ones who liked book 1. So they're going to be more likely to like book 2. And on that basis, I said, well, like whatever, 4.4 going up to a 4.6, that doesn't really bode well for book 2, given that the population of people who read book 2 are probably people who read book 1 and liked it. If it was like 4.8 or something, I might have read it. So I didn't read books 2 or 3, didn't finish the trilogy, and moved on to something else. But so you have to be a little bit careful with these star rating scales. And that's to say nothing of the like fake ratings that are an issue these days and all that. So little aside there, I suppose, but just I think it's important to point out that just because you see a ratio doesn't mean that it can be compared to whatever other ratio you want to compare it to, or just because you see a percent doesn't mean it can be compared to whatever other percent you want to compare it to. You have to think a little bit more deeply about whether making such a comparison is reasonable. And in these kind of scales, I think mathematically speaking, as well as, more generally speaking, it doesn't make a whole lot of sense. So we'd want to take each of these as what they are, or what we'd want to do is try to find a rating scale that maybe is common between all 3 of them. Can I get something like a rating out of 5 stars from all 3 sites? Does that information exist out there? I'd much rather deal with that information so it's consistent across all 3 than try to convert between information types. Okay, any questions on 6.1? Basic ideas of percent, what a percent is, and converting between fractions, decimals, and percents. Any questions on that? Okay, so then moving on to 6.2. Okay, so solving general applications of percent, we're going to start with solving equations that involve percents. And these kind of come in 3 types. So the first type is what percent of A is B. Or B is what percent of A? Or we can say what number is P percent of A? Or the number A is P percent of what number? Or P percent of what number is A? So here P is a percent and A and B are numbers, or like, for instance, whole numbers or perhaps decimals or fractions, but for the moment, we'll think of them as like natural numbers. So what percent of A is B? So here I'm looking for a percentage. I'm looking for P. So I have P times A equals B, and I'm looking to solve for P. What number is P percent of A? Well, here I have a number, let's call it B, equals P percent of A. So P times A equals B, but here we're solving for B. Or the number A is P percent of what number? Let's call this B. And here I have A equals PB. Maybe I should have called this, maybe I should have said the number B is P percent of what number so it's consistent, but A is P percent of what number? So we're looking for this one here. So we see that if I have the equation P percent times a number equals another number, there are three different options for which one of these could be unknown and which other two are given. Now, if I have P times A equals B and I want to solve for P, then I have P equals B divided by A. If I have P times A equals B and I want to solve for B, well, I just have B equals PA and I just perform the calculation. And if I have A equals P times B, then P is A over B. Okay, so let's look at a few examples. So I might ask a question like, what number is 7.5% of $330? Right, if I buy something that costs $330 and there's 7.5% sales tax, I might be asking, how much sales tax do I need to pay? What number is 7.5% of 330? So the is kind of separates the two sides of the equal sign or the one expression from another. Let's say that what number, the variable we're looking for, let's call that x. And 7.5% of usually indicates multiplication. So I have x equals 7.5% times 330. Now, nicely enough, I don't really need to do much to solve this equation. I don't actually need to do any equation solving steps. I just need to construct the equation, see that my variable is already isolated, and then just simplify. So 7.5% times 330. Well, I guess there's a couple ways I could approach this. I could make this 0.075 times 330. I can maybe be a little slicker. This is 7.5 divided by 100 times 330, or that's 7.5 times 330 divided by 100, or this is 7.5 times 330 divided by 100. Right, I could kind of shift that 100 over underneath the 330, and 330 divided by 100 is, move my decimal point to the left, 3.3. I think this will make my multiplication just a little bit easier. So 7.5 times 3.3. And I just multiply these out. 3 times 5 is 15. 3 times 7 is 21, plus 1 is 22. 3 times 5 is 15. 3 times 7 is 21, plus 1 is 22. So that's 2475. Then I need to adjust my decimal point. I have one place here, one place there. So I need 2 decimal places in the answer. 24.75. Does it make sense that if sales tax is a little under 10% on a sale that's, say, a little over $300, 10% of $300 is about $30. My tax that I would pay is $24.75. That's kind of in the ballpark, right? It shouldn't be like $2.47, and it shouldn't be like $247, right? This makes sense. And let's throw a dollar sign on there for good measure. My tax on this purchase would be $24.75. So if I look at this question, 47 is 20% of what number? I kind of locate my is here. That's the word that's going to become the equal sign that separates the two expressions. It says one thing is another thing. These two things are equivalent. The one expression is simply the number 47. And what's that the same as? What's that equal to? 20% of something. Let's name the thing we're looking for X. So I have 20% times X equals 47. Maybe I'll convert this percent to a decimal. I have 0.2 X equals 47. So I flipped sides just to make it a little nicer. I'm used to writing the variable on the left-hand side. So I just exchange sides just to make it look a little nicer, a little more standard. And that 20% I chose to write as 0.2. Right, I just got rid of the percent sign and bumped my decimal point 2 places to the left. Right, 20% is less than a whole. 0.2 is less than a whole. If I went the wrong direction and got like 2,000, I'd know that that's wrong. I shouldn't have 2,000 wholes if I started out with less than a whole. Now I have number times X equals number. I just divide both sides by the coefficient of X. And I get X equals 47 divided by 0.2. So I've now isolated my variable. I just need to simplify this right-hand side. Well, I have a division problem with a decimal in the denominator. What do I do here? I want to get rid of my decimal in the denominator, so I move the decimal point one place to the right in the denominator, but I better do that in the numerator as well. My 47 or 47.0, I better move that decimal point 1 to the right. 470 divided by 0.2 becomes 2 when I move that decimal point 1 to the right. Or 470 over 2, that's like 400 plus 70 over 2. Or that's 400 divided by 2 plus 70 divided by 2. I recognize that as 200 plus 35 or 235. Right, so sometimes I try to, you can certainly do this in long division. That's perfectly fine. But sometimes I try to show you maybe a little bit of a slicker way to do something, or, here I can use some of my fractions knowledge to make this an easier division problem that I can just do in my head instead of having to go off to the side and do a long division problem. But I see that this is 235. Does it make sense that 20% of 235 is 47? Yeah, that makes sense. If I said that like 20% of, 20 is 47. Well, that doesn't make sense because 20% of 20 is going to be less than 20. 47 is more than 20. They can't be the same thing. Or even if I said that 20% of, 58 is 47, that's not even in the right ballpark, right? 47 compared to 58 is like maybe something like 80%. It's certainly more than half, not 20%. But something like 20% of 235, that does make sense. That does seem like it's about the right size. Three percent of what number is 12? So this is a similar problem to up here. But here we have 3.7% rather than an easier percent to work with. So I have 0. Oh, let me write it this way first. 3.7% times the number we're looking for, x, is or equals 12. So 3.7% times x equals 12. And remember, I can get rid of the percent if I move my decimal 2 to the left. 3.7% is like 0.3%. So I move my decimal point 2 to the left, get rid of the percent sign. Be really careful to keep that buffer 0 in there. Make it 0.037. If you get rid of that and make it 0.37, it won't be the same number. So 0.037x equals 12. And then let's do an equation solving step. We have number times x equals number. We divide by the coefficient of x. We do that on both sides. So x equals 12 divided by 0.037. If I want to do this division problem, I need to move 1, 2, 3 places to the right. So I need to move by 12.000 to make a 12,000 divided by 37. Well, here I can do a long division. 12,000 over 37. Does 37 go into 12? No. Does it go into 120? Yes, it does. I think it should go in 3 times. 37 is about 40, and 40 times 3 is 120. 3 times 37. Well, 3 times 7 is 21. 3 times 30 is 90. 90 plus 21 is 111. 120 minus 111 gives me 9 left over. And bring down a 0. Does 37 go into 90? Sure, it does. Does it go in twice? 37 is a little less than 40. 40 times 2 is 80, so yeah, it will. Does it go in 3 times? No, I would need 111 for it to go in 3 times. It only goes in twice. 2 times 37, well, that is 74. I have 16 left over. I'll bring down my 0. Does 37 go into 160? Yeah, sure it does. I know it goes in at least 3 times because 3 times 37 is 111. What is 4 times 37? Is that more than 160 or less? Well, I know 37 is a little less than 40, and 4 times 40 is 160, so it will go in 4 times, but probably not 5. What is 37 times 4? That gives me 148. And 160 minus 148 is 12. So I could write this as 324 and 12 37ths. Or maybe I'll just say that this is approximately 324. 12/37 is less than a half, right? 12/36, 12 times 3 is 36. So this is like just about a third. So it's almost like 324 and about a third. Well, that's going to round down if I round to the nearest whole number. So I could either write it this way. If I wanted to, I could carry this out, 12,000.00, whatever. I could get more decimal places of accuracy. But I probably suspect that with the 37 in the denominator, that's a prime number. It's probably not going to mesh very nicely with anything in the numerator. This is probably going to be a decimal that that ends up repeating. And it's probably going to take it quite a while to repeat. So I think for this one, I would probably just give an approximate answer of about 324. And to be clear, if it was a WebAssign question, it would say very clearly, round your answer to the nearest whole number or something like that, right? So if I was making this, or choosing a problem like this for WebAssign, I would pick one that said round your answer to the nearest whole number, or I would pick one that had kind of a nice calculation to do that would terminate pretty quickly, like this one up here, that we don't even really need to do the long division to get the answer. Any questions so far? Okay, so let's look at another one of these. What number is 23% of 112? So x equals, I don't like writing percents in equations, so I always just like mentally immediately switch it to a decimal. X equals 23% of times 112. So again, I see that my variable is already isolated. I just need to do a simplification here. So I have 23% times 112, or I can move this decimal place 2 to the left and get rid of the percent. So 0.23 times 112. And if I carry out this multiplication, remember when I'm multiplying by decimals, I basically ignore the decimal for most of the computation and then just put it back in at the end. 3 times 2 is 6, 3 times 1 is 3, 3 times 1 is 3, 2 times 2 is 4, 2 times 1 is 2, 2 times 1 is 2. And then I add down, so I get 2576. I have 0 decimal places in 112, 2 in 0.23. I need to have 2 decimal places in my answer, 25.76. I know that 23% is, say, about a quarter, and 112 is about 100. A quarter of 100 is 25. So 25.76 seems in the ballpark of what I'm looking for. So that seems like it's about right. Okay, what about this one? 32 is 25% of what number? 32 equals 25% times x. Or I have that 32 equals 0.25x. And I see I have number times x equals number. I need to divide by the coefficient of x. So divide both sides by 0.25. I'll also switch sides here. X equals 32 over 0.25. Now, something that I might recognize here that can make this a little easier, I could move my decimal point to the right on the bottom, make this 3,200 divided by 25, and go this route. But I might happen to recognize that actually up here, if I recognize this really early, I could save myself quite a bit of work. Well, 25%, I might recognize that as 1/4. 25% of a whole is a quarter. This is just 1/4 x. I can actually see that I can just do an equation solving step here, multiply both sides by 4. So x is 4 times 32. And 4 times 30 plus 2 is 4 times 30 plus 4 times 2 with the distributive law, or 120 plus 8. I can get my answer a whole lot quicker this way than doing 3,200 divided by 25 in long division. If you didn't see that and you went the long division route, if you went this way, it wouldn't take too terribly long. It would just be a bit more work. But I always want to kind of keep my eye out for, if I'm working with percentages, is this percentage a nice ratio? 1/4 or maybe 75%, like 3/4. Will that make my problem easier? A percentage like 23%, that's not going to be a super nice ratio, but 25% is pretty nice. Right? If I see that I have 10% of something, that's also pretty nice. 1/10, right? That's pretty easy to work with. Okay, let's jump down to these applications. We'll skip over this one. So let's jump down to these applications for our last 13 minutes or so of class. Okay, so an example. When Hiro and his coworkers had a lunch at a restaurant, the bill was $90.50. They want to leave 15% of the total bill as a tip. How much should the tip be? And if they wanted to leave 20%, how much should it be? That is a typo. If they wanted to leave. Okay, so I want my tip. Let's call the tip. My tip should be or 15% of the total bill. So my tip is 15% of the total bill. Tip equals 15% times, well, the total bill was $90.50. So 15%, I can do 0.15 times 90.50, and I can carry out this computation. It might not be a bad idea to just do this for practice. So I'll leave this as an exercise. Or for my second question, how much should the tip be if they wanted to leave 20%? My tip would be 20% times 90.50, or it would be 0.20, or just 0.2 times 90.50, or just 90.5. I'll leave this as an exercise too. So this isn't a bad exercise to practice multiplying decimals, but we're going to do it in a slightly slicker way. Okay, what if we wanted to leave a 10% tip? Let's, we're not going to be mean to our waitresses, but just hypothetically. So 10% tip. I have T equals 10% times 90.50, but 10% is just 10 over 100. That's just 0.1 times 90.50, or that is 1/10 times 90.50. Well, I see that 90.5 over 10, that over 10 just moves the decimal point 1 to the left. So if I wanted to leave a 10% tip on a $90.50 check, I would leave $9.05. Does this pass the reasonability check? My bill was nearly $100. If I want to leave 10%, my tip would be a little under $10. That makes sense. If I want to leave a 20% tip, what would I do? Well, I noticed that a 20% tip is just twice a 10% tip. So this is double 10% tip. So my tip would be 20% times 90.5, or that's just 2 times 10% times 90.5. Or that's 2 times 1/10 times 90.5. But I know that this bit is $9.05. Right? Leaving a 20% tip is just double the tip that I would leave if I left a 10% tip, and 10% tip is really easy to compute. So I figure out what would a 10% tip be, $9.05, just move the decimal point one place. And then if I want to leave a 20% tip for a pretty good service, I would double it. 2 times $9.05, I double the dollar, the whole dollar amount to 18, double the cents amount to 10. If I wanted to leave a 20% tip, I would leave $18.10. Now, what if I wanted to leave a 15% tip? This is kind of a common, like, if you did good enough, you get a 15% tip. If you did pretty well, you get an 18%, and really well, or if the person's a good tipper, they maybe leave you 20%. So 15% is kind of a standard, I suppose. So here T would be 15% times 90.5. Well, 15% is 1.5 times. This is 1.5 times a 10% tip. Or 1.5 of something is 10% tip plus half of a 10% tip. So I can figure out what a 10% tip would be, figure out what half of that would be, half of that amount, and then add those two together. So this is like 1 plus a half of a 10% tip. Or it's like one amount of 9.05 plus a half of 9.05. So I'd leave $9.05 plus half more of that. Half of $9, well, that's $4.50. So like $4.53, something like that, if we round up, approximately. Or that would be $13.58. So if you want to compute a tip at a restaurant, you start off the basis of a 10% tip, because that's easy to compute. You just shift, you take your bill, you shift the decimal point one to the left, that's $9.05. That would be a 10% tip. If you want to leave 20%, you just double that amount to say $18.10. If you want to leave a 15% tip, you leave that amount plus half of that more, so about $9 and then another $4.50. If you wanted to leave something like an 18% tip, probably what I would do is, I mean, you could either break out the calculator at that point, or you could just say, well, 20% tip, 18% is like 20% minus 10%. I might leave this amount minus 10% of this amount of $18.10, something like that. Or kind of, you can figure out a 15 and a 20% tip and leave something in the middle. Plus or minus a few cents is not going to make or break your server's night. So if you say something between $13.50 and $18, if I leave like $16.50 or something, that's probably in the ballpark of an 18% tip. Any questions on any of this? Okay, let's look at one more example and then we'll save these last couple for next time. So Charisse deposits 8% of each paycheck into her retirement account. Her last paycheck was $1,485. How much did Charisse deposit into her retirement account? So she deposits 8% of each paycheck. Her deposit equals 8% of paycheck amount. So deposit equals 8% times her paycheck amount, 1,485. Or this is 0.08 times 1,485. So we do this multiplication. 5 times 8 is 40, write the 0, carry the 4. 8 times 8 is 64, plus 4 is 68, write the 8, carry the 6. 8 times 4 is 32, plus 6 is 38. Write the 8, carry the 3. 8 times 1 is 8, plus 3 is 11. So I get 11880. And then I have to insert the decimal point. So I have 0 decimal places in 1,485. I have 2 decimal places in 0.08. I need 2 in the answer, 1, 2. So this should be $118.80. And again, does this make sense? 8% is a little less than 10%. 10% of 1,485, that's, 1,485 is about $1,500. 10% of that would be 150. Is this a bit under 150, 120? Yeah, sure. Right, it's in the ballpark. It's not like $11.88 or like $1,188. Those would be clearly incorrect. But it seems about right. Any questions on any of this?